me. I'm Jana, and I'll be here as tech support during the tutorial. I want to introduce you to our tutor, Kristina Host. She's a research assistant at Faculty of Informatics and Digital Technologies, and she will hold the Google Colaboratory in Python Deep Learning Basics for CV Task tutorials. Enjoy.
Thank you. Can you just share me the link to the participants? I sent it to you in chat so they can.
Just a second. Did it arrive?
Okay, thank you.
You're welcome.
Okay, hi everyone. My name is Kristina, and I will present the topic. Just a second. Okay, and I will present the topic of deep learning basis for computer vision task. We will cover in this tutorial some introduction to Google Colaboratory, just some Python basics for images, and we will get in touch with convolutional neural networks and create a simple convolutional neural network for image classification. Just a little about me. I'm a PhD student and research assistant at the Faculty of Informatics and Digital Technology at the University of Rijeka. And my domain and the projects I work on are regarding automatic recognition of action and activities in sports. My focus is on handball, and if you find this interesting, you can contact me and I can get in touch with my mentors so we can maybe collaborate and similar. So human action recognition in handball is a supervised learning task. Why this is important? Because we are going to do that today, but in a different example, we are going to not classify actions that are happening in handball like I'm doing, but we are going to classify different images into different classes. So we can start, but with this introduction to Google Colaboratory, we will do some topics like how to create a new interactive notebook, how to connect to the virtual machine, how to enter some text, how to type a system command, how to type and run some Python code, how to save a notebook. This is like the basics. And then we will do some like basics in Python, how to load libraries, how to display an image, how to change some pixels, rotate an image and similar. This is like useful because in convolutional neural networks, you need a large amount of data. So sometimes it's useful to augment this data set that you're working on so you can make some changes on the images. Then we will cover what is a convolutional neural network and do one example on CIFAR-10 dataset. We will cover how to create a model, what are activation functions, what are filter and similar, how to train a model and how to test a model. We will use different libraries like TensorFlow and Keras. That TensorFlow allows you to train and run large neural networks. And Keras is also an API for deep learnings and allows you an easy training of neural networks. And it has like an implementation into TensorFlow, so it's useful. So let's start with the first part. What is Google Colaboratory? This is a free Google platform that offers you Jupyter Notebook virtual environment. Jupyter notebooks are like interactive notebooks where you can write also some headings, text, put some images, and also your code and execute it. Uh, you only need to have a Google account, so I hope everybody does, to sign in, and then you can use this Google Colaboratory. Google Colaboratory allows you to write and execute Python in your browser. Today we will work in Python, but I think now it can run also R. So if you use that, you also can use Google Colaboratory. Why is it useful? It's useful because we have access to GPUs and TPUs free of charge. I think you have a limit of 14 hours and for running a code in one session, but if you need like more time or more GPUs and similar, you can purchase additional computer units. So I think if you are like working with some machine learning or deep learning, you can use this Google Colaboratory to have like this GPUs and TPUs free of charge. Okay, so I invite you now to open on your Google account Google Colaboratory. If I'm going to fast, please slow down. Tell me to slow down. Okay, so you need to write Google Colaboratory in your browser. This Google Colab and click on it, open. I'm logged in, so I can access all my files that I have from before and create a new notebook. If it's not like this, please log in with your Gmail and then create a new notebook. It's in Croatian for me. I will convert it to English. Just a second. Okay, I will give you a minute to sign in. So do it with your Google account. Okay, here you can write the name of the file that you will save somewhere. It automatically saves on your Google Drive. But if you want to download it and something, you can also do it. So we can call it DSC Europe. For example. So if you want to open something or download it or rename it or save a copy or put it on GitHub and similar, you have these options in file. If you want to download it, you can download it in this format that is like the interactive notebook, or you can download like Python file. you can see here that you can add code and text. So let's add some text and write the title. If you want to write a title, you'll put a hashtag and then the title that you want. If you want another level of the title, just put more hashtags. I will write introduction to Google Colab. If you want to remove something, you just go here, select this pin. Okay, more important stuff before we start. If you want to use the GPUs, you have to go to runtime and then change runtime type. And then select the language you're working on, Python, and from CPUs, select GPUs because we are doing neural networks later, so we will need this. And you press this connect to connect to these GPUs. Okay. Maybe before we begin, the tech support sent you a link for where is the presentation and where are two files. One is called book and the other is called live. So please, if you can download these two files to your computer so we can work with them. So in the link that the tech support sent to you, please download the two images, the book and live image. Okay, so now let's start with this. So if you want to add some code, just press on this plus the code wherever you want to put it. And let's start with some basics. For example, how to check the version of Python we are working on. So when we want some system commands that we want to run in Google Colab, for example, we need some library or something that needs to be installed to check the version and similar, we have to use the exclamation mark in front and then write what we want. For example, Python and then version to check the version in which we are working on. So if it's a system command, we put an exclamation mark in front. If not, we are just like writing Python code. For example, A equals to, I don't know, 10 and B equals to 20. Let's see what is A plus B. So to run something, you press on this cell here, or you can go to runtime and run all, run before, run the focal cell, run after, and similar. So when we sum two numbers, we have the result written. If you want to do a comment, you put a hashtag in the code, in the text. For example, And let's try a for loop. For example, we have another variable that equals to 0. And let's see. We are going to calculate the sum of numbers from 1 to 5. For example, for x in range from 1 to, we have to write 6 because the last number is not taken into consideration. What we want to do, we want to make a sum of them. So we will increase this variable c, like c plus that number, c plus x. And when we are done with this, we want to print our results. So if is 15. Okay, so here you can connect to your Google Drive. You click here on Mount Drive. If you need something from your Google Drive, but you can also upload images into your environment from your computer, and then you click on this upload to session storage. But if you have it like on your computer, not on your drive, you have to upload it every time that you are using this collab node. If you want to put them in your drive, you can use it every time and just like on the drive and take them from there. Let's upload this to images that you have. So you click here and then you find where you save them. Just a second. Okay, I will select both of them and upload them into the environment. So ensure that your files are saved elsewhere, because after the session ends, you can't use them. Okay, so once they're like uploaded, you can find them here and we can work with them. Something that is maybe useful, if you go to help, you have here search code snippets, and you can find different parts of code that maybe are useful to you for, I don't know, capturing data from camera, downloading something to your computer and similar. Let's write image. So we have like here for showing images with OpenCV. So press it to see what we have. So to work with, we first have to import OpenCV. OpenCV is CV to the label. And then to read an image, we have this function imRead, and to show it, we have imWrite, but in Google Colab, for some reason, it is not working. So we have to use this Google Colab from this library, Google Colab patches the cv.image show. So we can't import also that. Sorry. I can copy it. And we can read our image. We will save one in a variable called book, and the other in life. To read the image, we will write cv2.read, and then we have to write the path to the image. You can just copy the path here, just go to these three dots and copy. And do the same thing for life. Once you write the code, you can run it. Okay, to see the shape of the images, we can write life.shape. So we can see how many pixels we got and what is the depth of the image. So we have a depth tree, so we work with images that are in color. We have a smaller one, and let's show the images. So to show, we have this command. So it is cv2 in show and what we want to show. So first we want to show, for example, life. This is the first image, and we want to show the second one. I will clear the output so you can see the code. And we will show the second one. The book. So to make some data augmentation, you need to know how to make some changes on your images. So let's start with changing one pixel, how it looks like. For example, we're going to change the pixel on this book at the position 100, 100. So if we want to change it, we can see maybe first what is the value on that position. So we have three values. The first value represent the blue pixel, the second the green one, and the third the red one. If it's 0, it's black, and if it's 255, if everything is 0, then it's a black pixel, and if everything is 255, we have a final of a white pixel. So let's change it. That, for example, it's a red pixel now. Oh, sorry. So we will change it to 0, 0, 155. And then show again the image to see if we have changed the pixel. And if you look closely, you can see that the pixel exchange. I will clear the output. Okay. Let's now put this book inside the first image. So let's change, for example, a range of pixels. Example, life from 50 to 200, 175, and from 50 to 175. In this position, we want to add a book. Once we do that, let's see how it looks. A book like life. So we changed the first image with a second, so we put the book into. Okay, and now we'll do like some changes on this picture to know how to convert it in, for example, grayscale, how to change the dimensions and similar. Okay, so let's first resize and then convert to grayscale. To get the height of the image, we can get it from the shape that we look before. So we have it in life shape 0, index 0, and we have width. Okay, it's life dot shape from first. Okay, so let's try to change the dimensions to have the height 3 times smaller and the width twice as large. And then turn this picture to gray. We can save it in another variable, for example, life 2. And we can use the function resize to do so. What we want to resize, we want to resize the image that is called life. How we want to resize them, so we want to be 2 times larger, and we want the height to be 3 times smaller. But we need to have integers to work with that, so just put int in front of these values. Okay, and I think it have to be in parentheses the size itself. So like this. We will also change the color. It's the function converts to color. What we want to convert, we want to convert life to, and how we want to convert it. So you can hear like see what options are available. We will use VGR to gray to convert it in gray. No. We have to also show the image to see what we have done. It's called Life 2. Okay, so we have changed the dimensions of the pictures. You can also blur the image, you can rotate the image. Let's try, for example, rotating it. CV2.rotate. What we want to rotate, the image life 2. How we want to rotate it. But by, for example, 90 degrees or 180, how you want. And let's show the image. So we have rotated it. You can do a lot of things. You can change colors, change size, rotate them, blur them to enlarge your set. Add some noise and similar. Okay, so this is the first part. Maybe one more thing, maybe if you want to save the picture, for example, is cv2.write, and then you write the path where you want to save it. For example, here in the content, now, for example, the name will be rotated dot GPG, and what we want to save, we want to save the image name rotated. Once you run this, okay, I have something CV2 image, right? Sorry. Okay, you see here, if you refresh, that we have now the rotated file saved. But if you want to, it's better to save it on the disk so it's saved permanently. Okay, this is the end of the first part. And then we will start with convolutional neural networks. Maybe just I'd add a second title. No, convolutional neural networks, for example, this CIFAR dataset. And when you have like more titles, you can go on here and navigate through them. You can, for example, also press on this and then it looks like this. And we will add some code later, so we will not use this anymore. Okay, so let's get back to the presentation. So when we have a supervised learning we must have a lot of label data. And one of the most famous data set to get in touch with the field of computer vision is this T410 data set. It contains 60,000 of color images that are 32 by 32 pixels for each pixel. So we observe 3 colors. And we have pictures of airplanes, cars, birds, cat, deer, dogs, frogs, horses, ships, and trucks. And we want to classify these pictures into these categories. So each image is marked with a number from 0 to 9, representing one class. So we have a total of 10 classes, 6,000 for each class. We will use this one-hot encoding because it makes our training of data more useful and expressive, and it can be rescaled easily. So this is the data set we are working with. And now, what is a convolutional neural network? So convolutional neural network is a network that is often used in data that has images. And we have some computer vision tests that are good with convolutional neural networks. For example, image classification, object detection, mass segmentation, and similar. How the convolutional neural network works? So we have 3 types of layer. We have an input layer, we have hidden layers, and we have output layers. The input layer stores the value of the pictures. The output layers provides to us the probability to what is on the picture for the class. So if it's a dog, cat, deer, lion, and similar, what are the probability for that? And we have this hidden layer that in convolutional neural network are consisted of one or more convolutional layer, then we have some polling layers, then again convolutional layer, one or more, then a polling, and etc. etc. These convolutional and polling layers are used to extract some features. And at the end, we have fully connected layers. And these fully connected layers are used to classify images into the classes. So we have hidden layers that consist of convolutional, pooling, and fully connected layers. In the convolutional layers, we have filters that convolve with the image. So we have these filters that slide over the image specialist, so in the epsilon and x orientation. Filters are on the same depth of the input images. So if we have 32 by 32 by 3 image, the filter it also will be by 3, but of smaller size. So filter contains the weight that the network needs to learn and are smaller special units than the input image, but of equal weight. Each layer of the convolution usually consists of several filters, and the more filters we have, more features can be recognized. At the beginning, in like first convolutional layer, we can detect some edges, some contours, and similar. When you're going like deeper, then we can some circles and stuff like that. But deeper you go into the convolution, it can recognize like head of a dog, a wheel of the car, and stuff like that. And at the end, it can recognize like fully grown objects. These filters are activated in place where certain image properties are recognized. And it's like activated with some activation function. So we need to have activation function in order to activate a filter in a certain place. So we have different types of activation functions that decide whether a particular neuron is activated or not. The goal of this is to introduce nonlinearity because neural network without this activation function is simply a regression model. Today we will use this one, a ReLU that looks like this with 0 if it's less than 0 and it increases if it's more. What is also interesting is this padding. So when we have convolution, there are some pixels that are not taken in consideration so many times. For example, a corner or edge pixels in the image. So we can use padding to put zeros around these edges to make so that also the corner and the edge pixel are taken in consideration for the convolution more time. Because if you can see here, for example, this corner pixels, if we have 3x3 filter that is sliding through the image, it's taken into consideration just once. The edge pixel, the pixel B on the edge, is taken in consideration, for example, 3 times. And some pixel in the middle is taken into consideration in like 9 times. So if we add zeros around the image, we will take into consideration this corner and edge pixels more, because maybe something important is also in that part of the image. So because of this, we use padding. We have pooling. So I said that we have convolutional layers and that we have pooling layers. Pooling layers are used to reduce the resolution of the feature map or activation maps that are the results of the activation functions. So are the results of the convolution process. So we have to use this pooling to reduce this resolution. We have two most famous type of that is the average pooling, when a group of data is replaced with the arithmetic mean of the numbers, or max pooling where we find the maximum to pool these feature maps. We will use today this maximal pooling. What means this? So max pooling with 2x2 filters. So we are having a filter that takes into consideration 4 pixels and then finds maximum. And what is try to, because if we have 2x2 filters, we look at this 4 and we don't have to consider them, and then we skip we're not going like sliding for 1 pixel, but we are sliding for 2 pixels. So this stride is for how many pixels we are moving through the image. This we need also for the convolution and for the pooling. But in convolution, it's usually 1 because you are like moving for 1 horizontally and 1 vertically. But when you're doing like pooling, you go by the filter size that you defined. Okay, this is the architecture we will create. So we will create 2 convolutional layers of filter that have 32 filters that are 3 by 3 of size 3 by 3. We will have stride 1, so we will move around the picture for 1 pixel. We will have then a max pooling layer, then a dropout layer. So we'll take a percentage of filters and like remove them to do the second convolutional, the third and fourth convolutional layer, and again a max pooling, then again dropout, and at the end we will have fully connected layers that are used to classify these results that we have. So let's start. We have to get back to Google Colab to do so. Okay. So we will use the C510 dataset, and we will load that from Keras. So you can write, maybe I will show you Keras dataset C5. So you can see here how it looks. The data set is already splitted between training and testing set, but you can also like split it further to have validation and similar. Okay, so we can copy this part to load the data set, but before that we have to import the libraries that we need. So we will work with TensorFlow. It usually is like TF, so import TensorFlow STS. And we have this implementation of Keras and TensorFlow, and we will use it. So from TensorFlow, import Keras. Okay, so learning the parameters of a prediction function and testing it on the same data is a methodological mistake. So a model will just repeat the labels that have learned, that have seen, and it will have a perfect score. So it will fail on predicting it on some unseen data. Because of that, if to prevent this, this is called overfitting. So if the models is like familiar only with the images that he has seen, but we want our model to perform like good also on some unseen data. So we like cut from the data set a part of the data and put it in this testing set. So when we test our model, we tested on some unseen data. So we have, if you have copy this, we will have for variables, we will have xtrain, where we have the values of the pictures, of the pixels in the pictures. And in epsilon, we have the labels for each image. The also is in the test set. So we have a training set and a test set. We can run this and see what are the dimensions. For example, in x train dot shape. So we have in the training part, we have 50,000 of images that are 32 by 32 pixels and are in color. Okay, let's see how the labels look. So we have for each of this, for each of this, we have one thing, just a label for every image. In the test set, we will have like the other 10,000 that remain for the test. How the labels look. So Epsilon train, for example. Okay. This is for every picture, the label. For example, if you want to see just the first one, we will see that is 6. Let's try another library to show the images. So we work with OpenCV. Let's like try to show an image with a matplot library. So let's import matplot lib.pyplot. And let's show the image. Let's show the first one. So the first one have the index 0. The second one, it will have the index 1 and so on. So I have here a picture of a frog. We can do some print. The class of the first image is in epsilon train. Is the label 6, that is a frog. If you want to show the second one, you will just put here 1. Let's show the first 5. So we'll use the for loop as at the beginning of section. So for example, in range from 0, because the first image is on index 0, to 5, because the last one we don't take into consideration what we want. And so you can, with matplot library, use some subplots to plot like more things. So we will use subplot. Then you write like the number of rows, the number of column, and the position where you want to start. To change this, we can like add the value of E that is for the 0, then 2, then 3, and so on, to like show different image in just one row. Okay, we will show the image. So in show, what we want to show, we want to show the images from 0 to 4. That is in I. Okay, and at the end we have to show everything, and we obtain like the first 5 images that we have. So like I mentioned before, one-hot encoding makes our training data more useful and expressive, so we will use that to do it. There is like a function that do that. It's called toCategorical. So we will define epsilon train 1 hot and epsilon test 1 hot. So we have to change also the training and testing variable where the label is saved. And we can do it from keras dot utils dot and then write to categorical. What we want to do it with epsilon train, and we want to have 10 classes. The same thing we are doing for the test set. So we want to do it with test and have 10 classes. How it looks. So for example, 1 train 1 hot, for example, the first one. So we have zeros and ones. So 1 is on the position of that class, and the other are 0. If you look at everything, so we have like this. Okay. This data, when we are like working with images, or when we are like working on some data values that are not in common scale, we use normalization. Normalization is important because it ensures that each input parameter, is a pixel in this case, has a similar data distribution. This makes the convergence faster while training the network. So in this case, we have images saved with the values of picture from 0 to 255, and we want them to be between 0 and 1. So we will normalize these data. So we will have X train change. We will change it like X train to be divided by 255, but we have to change the type to be float. And we have to do that also for the test set. So X test also divided by 255. This part is called normalization. So we will have the values between 0 and 1. Okay, so here we have finished with data preparation. So we have our data and now we can create the model. We can also just show how it looks like now. So we have, it's not divided. Why is not divided? X trained. I didn't run it. Okay. So this is like how it looks before. And now when we divide it, we have like float values, decimal values between 0 and 1. Okay. Don't forget to run your code. We will now create the model that we saw before. I will put a heading, creating a model, a CNN model. Okay. So first we have to define our model. We will call it model. And from Keras, we will take a sequential model so we can sequentially like put every layer inside. So keras.model models dot sequential. And it's empty at the beginning. Every line that we like make, you have to run just once, because if you like run it more time, you will create more layers. So like run every line just. So let's create the first convolutional neural network, convolutional neural layer. So to add layers, just put model dot add, and then you select one what you want to add. So it's keras dot layers. And then you have like a lot of layers that can be added. We will use a convolutional 2D because we are like working with images. And then you have to define the number of filters. So we will have 32 by 32, 32 filters that are of size 3 by 3 pixels. So this kernel size. Then we have strides. So for how many pixels the convolution like will happen, like the filter are like sliding for how many pixels horizontally and vertically. By default is 1, so we don't have to write this. We have to add, if we want, padding. So to add zeros around the image. So if it's valid, if you like write valid is no padding, but if you write like same, it adds as many zero as needed. So here we like add zeros. For every layer, we have to define the activation function. For every layer of the convolution. So the activation will be relu, like I said before. And what you do in the first layer, you have to define the input shape for the network. So it will be the input shape of the images that you have. So we have 32 by 32 images. Sorry. So input shape is 32, 32, and 3. This is our first convolutional layer. You can run it. Okay, I have one missing parenthesis. Okay, so this is the first layer. Only in the first layer you have to define the input shape, and in the others it's like the network takes it from the one before. So everything will be the same, but we don't have this input shape. And this will be our second one. So also we have 32 filters, 3 by 3. We add some padding. We have the activation value. After that, we have to use a polling layer. So the process is similar, just we will take another type of layer. So it's called max polling. We are working with images for max poll 2D. And we have this to define the pool size. So how many pixels we will take into consideration to find the maximum. So this is this part. And we will take 2 by 2. So we have to write pool size equals to 2 by 2. the fourth layer that we use is dropout layer. So in each pass during training, we want to exclude a certain percentage of our neurons or filters in order to be less sensitive to changes in input data. And in this way, prevent overfitting. So we're like taking the picture and we like drop out 30% of the features found on it to make the model better to recognize something on the image that it doesn't haven't seen before. So on some not seen data to perform better on non-seen data. So we will add a dropout layer. So keras.layers dot dropout. And we write like how the percentage of what we want to be rejected. So we want 25% of randomly selected. Okay. Then again, we have layers with convolution and max pooling. So you can maybe just copy this and then change. So now we will have 64 filters. So we are like, deeper we go, we increase the number of filters. So we have two convolutional layers. Then we have max pooling layer. And finally, we have, again, a dropout layer. Okay. Now we are like done with the layers with the convolution to extract the features. And now we have to use some fully connected layers to do the classification. A second. So we have convolutional max pooling layers with a dropout to prevent overfitting. And this was for feature extraction. And now we will use some fully connected layers to do the classification. But first we have to flatten this data because the layers in neural networks take 1D dimensions. So first we will add a layer that likes flatten this data to 1 dimension. keras.layers dot flatten. And then we can add our first fully connected layer. We want to have 512 neurons. And again, we have the activation that is Relo. And in the final layer, we use a different activation function to classify the images. But before that, we will use another dropout. You can copy. So to randomly choose, we will take 50% of neurons to discard. So this is drop-off layer of 50%. And we want to classify the data. And to classify, we will use a function that is called softmax, that is used when you have more categories. For example, when you have like us 10 categories, we use this activation function that is called softmax. So we are putting the fully connected layer called dense, and we are like taking 10 neurons, so the number of classes that you have, and the activation. So at the end, we use softmax, that is for classifying. To see at the end how our model looks, we can show it so you can see how our layers looks here, how many parameters we have, and similar. I hope everything works. Okay, if yes, we can continue. So we have created the model, then we have to compile it. Compile. We are doing that, like we have to define the loss function that will be used. For example, cross entropy or mean square error and similar. We have to define the optimization method, for example, Adam optimizer or stochastic gradient descent and similar. And we have to define a metric that we want to monitor, for example, accuracy. So we write model.compile. We define the loss. So we have 10 different classes. In that case, we use categorical cross entropy. If you like have a binary problem, you will use binary and similar. So categorical cross entropy. Then we define the optimizer. It will be, for our case, Adam, that is a combination of two very good of them. And you can then define the metrics that you want. We will just follow the accuracy. The second step is to train the model. So we created the model, we defined how we want to compile it, like what we want to follow accuracy, how we optimize the model, and what is the laws that we are like following. And then we have to define how we will train the model. We like train the model with model.fit, but we will save the history of the model in a variable so we can visualize the results. So first write history, for example, history of model equals to model.fit and what we are fitting inside our model. So first we have to put the data for training the model. This will be x train and epsilon train 1 hot. So the data for training the model. Then we have to define the batch size. The batch size is the number of training data used during one iteration. So it's the number of samples you work on before updating the model. So this is like batch size. So the size of a batch must be more than or equal to 1 or less than or equal to the number of samples. Usually it's like 32 or 44, so we will use 32. Batch size equals to 32. Then you have to define the number of epochs. This is like the number of complete passes through the training set. So one epoch consists of multiple batches. Epoch is like for how many iterations we want to train our model. We can here put like, for example, 15, because we don't have a lot of time, but you can like put more and see how the result will be. And you can also define some early stop. For example, if the loss is like worse, stop training. Okay. And one other thing that we have to put here is the validation set size. So after every epoch, we want our model to test its performance on a part of the data that it have not seen. So this part we called validation set. So we are taking a part of the training set and like leave it out. And then after every iteration, so after every epoch, we validate our results on this set. So validation, if you have it like defined before, then you will took this validation data equals to something that you have defined. If not, you can take a percentage of the training data. You can do that with this validation split. So we will take 20% of the data, so 0.2. Okay, once you write this, you can run it. I hope you changed the runtime type to GPUs before. If not, maybe just interrupt restart runtime, change the runtime type, and run it all again. If you have like defined to use GPUs, you can run our model. So it trains for 15 epochs, and we will see the result. So you can see here how our loss is performing and how is the accuracy, validation accuracy for the first epoch. So we have validation accuracy on this validation set that we have defined of 57%. So this is the accuracy that is increasing. So we have in the second epoch 64% of accuracy, then 66, 71, etc. And you can see that the validation loss is falling. So we have less mistakes. It's good to train it like to have like better accuracy. If you want to have better accuracy, you have to train it more, but be aware of the loss, because if you have like a lot of mistakes, is not good. So you have to monitor the loss to decide where you will stop training. If the loss is decreasing, it's good, but if it's like increasing, then maybe the model start to overfit and it's time to stop training. Okay, we will see the results for our 15 epochs, and then we will monitor our results. In this history of model variable, we will have a dictionary with the values of validation and accuracy. And we can plot this. So let's see how the results look like. We have a function that does this for us. So we will just import it. We will use it from pandas. So it's called data frame, and we put the name of the dictionary where we have the values dot history, dot plot, and you can also define the size of the figure that you want to display, but is optional. We will put 8. Okay. We want to show the grids. So plot the dot grid. It's true. And we want to write on the x-axis the label that will be epoch. And then we want to show everything. To see the results. So this is on one graph, our validation loss that you see is decreasing, and our validation accuracy that is increasing. So you see here that the validation loss is like decreasing, and maybe you can try to train it more because we don't have like big oscillation of the validation loss. Okay, I will like put again here the code. I will clear the output so you can see it. Okay. We will save the model. So you can define different conditions when you want to save the model. We will like save it here after this 15 epochs. So we just write model.save, and you like write where you want to save it. I will just give it a name. And extension is .h5 for our model. So the model is saved. Okay, I have a problem. Okay. I will run everything one more time from here. Runtime run after. Okay. Run. Okay, I hope it will work. If not, I will like show you what you can do more, and you will like try it yourself. Okay, so we save the model, but I save it like in this environment and I cannot upload it now. After training, we have to test our model. So after training, we have testing. And we do it with model.evaluate. And we want you put on which data you want to evaluate your model. We will evaluate it on the test set that we have defined at the beginning. So it is X test and epsilon train one hot. You can run this. So first you have the loss data, and then you have the accuracy for the model. Please try that. I will try it later if it will work for me. And we will save the prediction for that model. So we will write a new variable where we will save the prediction. It's model.predict. And we want to predict what? We want to predict the labels for the pictures that we have. So it X test. If you want to see, for example, the prediction for the first picture of the testing set, we will take the first one. Okay, so it will be, I hope. This is like testing on the test set that we defined. And we will also test it on your own image. Okay. So to test it on another image, you can like upload it to the system, or we can do this with curl that you have in the code snippets that we like checked before. And so, for example, you can write curl to take a picture from some link. So just like Google, I don't know, an image of a cat or I don't know, a frog or something that we have. For example, I will look for a cat. Or you can download it and then I hope it will work. I'm not sure. So is curl then -0 -O, and then like the name of the picture, cat picture, for example, dot. No, it's for me it's really slow because I cannot use GPUs, so it will take some time to try and test it for me. Then you put a link that you have. Now this will not work. It's to start with. For example, this one. It must be in the correct format. In this way, we will save in this environment picture in this with this name. And for example, uh, with Matplot library, we can read the image. The important part is that we have to resize this image to test it because we have 32 by 32 pixels. And in our case, this is, I don't know which image is selected, but is not in that form. So you have to resize it. This is the important part. So to test some images and similar, you have to resize it to fit the model. So we have a function resize. What we want to resize, we want to resize the image X and we want to resize it in 32 by 32. Okay, you can show this image. Wait, for example, put dot in show. Sorry, I didn't import the library for this. So you can use it from CV2, for example, but is differently written. This is from sk image dot transform import resize. So you can see how slow it is when you don't use GPUs, so use them. I do also different projects on this, so I run out the memory. Okay, and once you show the image, you can make the predictions to see the probabilities for each class. We can do it like probabilities for these pictures. For this one picture. So model dot predict, and we predict it on this precise picture, but we have to convert it into an array to do so. So to do so, import numpy s and p, and then we want it from resized. To see these probabilities, just print them. Okay, and to make uh like a visualization, or not visualization, but to see like the probabilities to be a cat, a frog, and similar. Let's like define class names to write it. So class names, you have to write it in the order, in the right order. So first we have the airplane, then we have the car, then we have the bird, then we have the cat, the frog, no, cat, then a deer, deer, then a dog, then a frog, then a horse. After that, we have a sheep, and then we have a truck. So this is our 10 name of classes. We want to sort the probabilities so we can like display the results. So we'll sort the indexes in the probabilities. We can do it with arg sort. What we want to sort the probabilities. And we have to define this 0. So we want to take the first row and everything in that column, because we have that double parenthesis in the labels. Here, when you print it, you will see that we have like double parentheses. So we have to put it like this way. And we want to print the names and the probabilities. So for in range from the one that has the highest probability, we want to print. So we go from 9 to 5, decreasing. We want to print, so the class names of the indexes. So the probability for this class name will be, this is the part that we print, probabilities. So again, this, because of the parentheses, 0, and then the index. So we are going through every class. I am missing here the S. Okay. Okay, I hope you can run this. I will like show on another script the results because I can't now open notebook. This is Europe. Okay. I think I have here the results. This will be the script I will give to you. So these were the results of the accuracy and the loss. We saved the model, we tested it. So the first is the loss and then we have accuracy on the testing data. We have 76% of accuracy on our testing data. We predicted the values for our testing set. This is how it looks for the first image. We downloaded a picture of a cat or a picture of something else, read that image, and then resize it. So because the size have to be as the input size, and then we obtain a resized image in 32 by 32 pixels. After that, we predicted the probabilities for every class, and we sorted the probability to have an output like this. So it is sure on this picture of mine that the cat is on the picture with 72% of probability. That is a dog with 14%. That is a horse with 5% and a deer also like about percent. So this is the result that you need to get at the end. Sorry about like this part, but the result will be the same. I will give you the script of this that we have done today. You have in the map also the presentation that we used, and I will put in this same map also the script that we work on today. So that's it. If you have any question, maybe you can write it down on the chat. That's it. I hope you learn something about convolutional neural networks and some maybe Python basics if you didn't know them from before. If you don't have any questions, that's it for today. You can contact me on my email that you can find on the presentation if you have something that you want to know or you want to, I don't know, work on the handball data set and similar.
Thank you, Kristina. It was very interesting. Thanks everybody for watching this tutorial. The next